Boundary layer flow. In the part 1, I had taught you what do we mean by boundary layer, then laminar and turbulent boundary layer, laminar sublayer, boundary layer thickness, and we also saw the derivation of displacement thickness, momentum thickness, and energy thickness equations. Today in this video, we will be deriving one Karman Momentum Integral Equation. We can also call this topic as drag force on a flat plate due to boundary layer. As seen in the diagram, we are having a thin plate and the fluid flows with a free stream velocity capital U. अगर हमें ड्रैग फोर्स या तो स्किन फ्रिक्शन फाइंड करना है प्लेट पे, तो हमें जो वेलोसिटी प्रोफाइल है नियर द प्लेट वो पता होनी चाहिए. And for that, what we are doing, we are just considering a small length dx of the plate at a distance x from the leading edge, which is as I have shown in this figure. और ये जो small length of plate जो हमने ली, whose length is dx, उसका enlarged view I have drawn in the figure B. The thickness of the strip is dy and its width is unity. We have taken a small length dx of the plate which is at a distance x from the leading edge, and here this is the enlarged view shown in the figure B. The first step will be to write the equation for shear stress, which is tau naught is equal to mu du by dy, mu into d capital U upon dy, and this is at y is equal to 0. अब हमें फाइंड करना है ड्रैग फोर्स या तो बोल सकते हैं कि shear फोर्स ओवर अ स्मॉल डिस्टेंस dx. तो dx के लिए जो ड्रैग फोर्स हो जाएगा दैट विल बी shear stress into area. Shear stress which is tau naught और area dx into 1 because width is unity. तो एरिया मेरा हो जाएगा dx into 1, length into width, which is dx into width. Width is unity. So this is the drag force that we have got. Then we already know that force is equal to rate of change of momentum. तो यहाँ पे भी हम लोग वही लेंगे that drag force will be equal to rate of change of momentum over the distance dx. अभी हम लोग सिर्फ डिस्टेंस dx के लिए फाइंड कर रहे हैं, और ये ABCD जो है दैट विल बी माई कंट्रोल वॉल्यूम, और स्मॉल u जो होगा दैट इज़ द वेलोसिटी एट एनी पॉइंट विद इन द बाउंड्री लेयर. अभी वी नीड टू फाइंड मास रेट ऑफ फ्लो. तो अगर मास रेट ऑफ फ्लो की बात करें तो BC में से मास रेट ऑफ फ्लो बाहर निकलेगा और फेस AD और DC में मास रेट ऑफ फ्लो विल बी एंटरिंग. So we'll write it like that: mass rate of flow entering through face AD, then mass rate of flow entering through face DC, and mass rate of flow leaving the face BC. मतलब AD और DC में से enter होगा and it will leave from BC. So now this will be integration from 0 to delta, that is up to boundary layer thickness, will integrate it. Rho into velocity into area of the strip of thickness dy. Thickness is dy और width जो होगी that is 1. Integration 0 to delta rho u dy. Then we have mass rate of flow leaving the face BC. तो वो होगा मास थ्रू AD प्लस डेल बाई डेल एक्स मास थ्रू AD इंटू dx. बिकॉज AD से BC तक का डिस्टेंस कितना है, dx जितना. दैट इज़ वाई वी टुक द पार्शियल डेरिवेटिव विथ रिस्पेक्ट टू x, del by del x mass through AD into dx. So we have got this integration 0 to delta rho u dy plus del by del x integration 0 to delta rho u dy into dx. Now as you can see this, mass rate of flow through AD plus DC is equal to mass rate of flow leaving through the face BC. तो हम लोग क्या लिख सकते हैं कि मास रेट ऑफ फ्लो एंटरिंग थ्रू DC कितना हो जाएगा, इट विल बी इक्वल टू मास रेट ऑफ फ्लो लीविंग थ्रू द फेस BC माइनस मास रेट ऑफ फ्लो एंटरिंग थ्रू द फेस AD. Then we'll just place the values here, which is integration 0 to delta rho u dy plus del by del x integration 0 to delta rho u dy into dx minus integration 0 to delta rho u dy. This rho u dy will get cancelled and we'll have mass rate of flow entering through face DC, which will be equal to del by del x integration 0 to delta rho u dy into dx. Now we have the mass rate of flow for AD, BC and DC, so we can go for finding momentum flux. So we have the momentum flux entering through AD, which will be equal to mass into velocity. So the mass rate we have already found, which is integration 0 to delta rho u dy, and the velocity is small u. So it will be integration 0 to delta rho u square dy. Then the momentum flux leaving the face BC, which will be again the same thing, mass rate into velocity. So the mass rate we have already found. Just we need to multiply small u with this and it will become rho u square dy plus del by del x integration 0 to delta rho u square dy into dx. Then the momentum flux entering the side DC, that will be equal to again the same thing, mass rate into velocity, but for DC the velocity will be capital U as free stream velocity will be entering. So we'll get it equal to del by del x integration 0 to delta rho u into capital U dy into dx. Now we can find the rate of change of momentum of the control volume ABCD because we have all the data needed. So the rate of change of momentum will be equal to the momentum flux through BC minus momentum flux through AD minus momentum flux through DC. This is how we'll find the rate of change of momentum for the control volume ABCD. We already have all of these three equations. Momentum flux leaving BC is integration 0 to delta rho u square dy plus del by del x integration 0 to delta rho u dy into dx. Then for face AD we have integration 0 to delta rho u square dy minus through face DC it is del by del x integration 0 to delta rho u into capital U dy into dx. Now this will get cancelled and we have del by del x, which we can take it as common, rho u into u dy minus integration 0 to delta rho u into capital U dy into dx. So del by del x integration 0 to delta, we can take rho as common and we'll have in bracket u square minus uu dy into dx. Then we can bring rho out and it will be rho into del by del x integration 0 to delta u square minus uu dy into dx. Now rho is a constant for incompressible flow. Now we need to compare both the equations, which is drag force is equal to rate of change of momentum over the distance dx. So it will be minus tau naught dx is equal to rho into del by del x integration 0 to delta u square minus uu dy into dx. This dx will get cancelled and we'll have minus tau naught is equal to rho del by del x integration 0 to delta u square minus uu dy. Now if on the right hand side I take minus as common, then this bracket will become uu minus u square. So I have taken minus common and this will be uu minus u square. Now what I am doing, I am taking capital U square common. So if I take capital U square common, तो मेरी जो फर्स्ट वैल्यू है विच इज़ u इंटू कैपिटल U, उसको मुझे u से मल्टीप्लाई और डिवाइड करना पड़ेगा, और जो मेरी दूसरी वैल्यू है स्मॉल u स्क्वायर, उसे मुझे u स्क्वायर से मल्टीप्लाई और डिवाइड करना पड़ेगा. So now the equation will become tau naught is equal to rho del by del x integration 0 to delta capital U square taken as common u upon capital U minus u square upon capital U square into dy. Now I can also bring this capital U square out of the bracket. So it will be rho u square del by del x integration 0 to delta u by u into, will be left with 1 minus u by u dy. Now we had already derived the equation for momentum thickness, which was integration 0 to delta u by u 1 minus u by u dy. So this is theta and we'll have tau naught upon rho u square is equal to del theta by del x. This equation that we have found, that is known as the von Karman Momentum Integral Equation for the boundary layer flow. Von Karman Momentum Integral Equation is tau naught upon rho u square is equal to del theta by del x. Now suppose I want to find the drag force on a small distance dx and my width is not unity, then the equation for drag force will be tau naught into dx into b. And अगर मुझे फाइंड करना है टोटल ड्रैग ऑन द प्लेट जिसकी लेंथ l जितनी है, देन जो मेरा टोटल ड्रैग फोर्स हो जाएगा that will be Fd is equal to integration 0 to L tau naught b dx. Now the next thing that we need to understand is local coefficient of drag, जिसे हम लोग CD star से denote करते हैं. Now the CD star is equal to tau naught upon 1 by 2 rho u square. That is, it is the ratio of shear stress to the pressure head and it is known as local coefficient of drag. Then we have the average coefficient of drag, which is the ratio of total drag force to the quantity 1 by 2 rho a u square. So it is Fd upon 1 by 2 rho a u square. ये जो दोनों इक्वेशंस है तो सेम ही, बिकॉज टाउ नॉट इज़ Fd अपॉन a. वही चीज़ को यहाँ पे लिखा है सेकेंड वाले इक्वेशन में, टाउ नॉट की जगह पे Fd अपॉन a. There are some boundary conditions for the velocity profiles and these boundary conditions should be satisfied for both laminar boundary layer as well as turbulent boundary layer zone. The first one is that at y equal to 0, the velocity is 0 and so du by dy will have some finite value. फिर जब y बाउंड्री लेयर थिकनेस जितना हो जाता है, दैट इज़ y इज इक्वल टू डेल्टा होता है, तब वी ऑलरेडी नो दैट द वेलोसिटी इज इक्वल टू फ्री स्ट्रीम वेलोसिटी विच इज़ u विल बी इक्वल टू कैपिटल U. एंड वन मोर थिंग वी नो विच इज़ कि एज ऑफ द बाउंड्री लेयर जहाँ पे होती है वहाँ पे माई वेलोसिटी ग्रेडियंट इज़ ज़ीरो, दैट इज़ एट y इज इक्वल टू डेल्टा du by dy will be equal to 0. So these are the three boundary conditions for the velocity profiles. Then the next topic is turbulent boundary layer on a flat plate. Turbulent boundary layer के लिए velocity profile का equation ब्लेशियस और प्लांडल ने दिया था एंड ऑल्सो shear stress का equation ब्लेशियस ने दिया था. So the equation for velocity profile given by ब्लेशियस for turbulent boundary layer वो एक पावर लॉ था which is represented as u upon u is equal to y by delta raised to 1 upon n. This was the velocity profile equation given by Placius. और यहाँ पे n जो है that will vary from 5 to 10 and it will depend on the Reynolds number. उसके बाद प्रांडल ने इक्वेशन दिया है for velocity profile for turbulent boundary layer, as per which जो velocity होगी it will vary with the 7th root of distance from the wall or plate. तो n हो जाएगा 7. So it will be u upon u is equal to y by delta raised to 1 upon 7. As per Placius, n will lie between 5 to 10 and then Prandtl gave that it will be 7th root of distance from the wall or plate. So n will be 7 and Reynolds number will lie between 5 into 10 raised to 5 to 10 raised to 7. Now if I say about this equation given by Placius, तो वो लैमिनार सब लेयर के लिए वैलिड नहीं है, बिकॉज आई हैव ऑलरेडी एक्सप्लेन्ड दैट नियर टू द बाउंड्री वेलोसिटी जो होती है इट इज़ ओनली इन्फ्लुएंस्ड बाय विस्कस इफेक्ट्स. देन एज आई टोल्ड दैट प्लेशियर हैड ऑल्सो गिवन इक्वेशन for shear stress on flat plate, and this equation was tau naught is equal to 0.0225 rho u square into mu upon rho delta u raised to 1 by 4. And here this Reynolds number is ranging from 5 into 10 raised to 5 to 10 raised to 7. Then there are few more equations that you need to remember for turbulent flow, which are, first one is for boundary layer thickness, which is 0.37x upon rex raised to 1 by 5. Then we have local coefficient of drag, which is CD is equal to 0.059 upon rex raised to 1 by 5. Rex, that is Reynolds number for length x, and rel is Reynolds number at the end of the plate. X is the distance from the leading edge, which we have already seen in the first part of boundary layer flow. So the average coefficient of drag is given by CDA is equal to 0.074 upon rel raised to 1 by 5. Then our x is the distance from the leading edge. Rex is the Reynolds number for length x, and rel, which will be the Reynolds number at the end of the plate. So these are the three equations that you need to remember for turbulent boundary layer on flat plate. Then there are few more equations that you need to remember. Here I'll be writing that based on the velocity profile. So velocity profile in laminar boundary layer, there are 5 velocity profiles, and for that we have the equations for boundary layer thickness, shear stress and average coefficient of drag. The first velocity profile is u by u is equal to 2 y by delta minus y by delta whole square. For this, delta, that is the boundary layer thickness, is given by 5.48x upon root rex, and tau naught is equal to 0.365 mu u by x into root rex. Then CD, which is the average coefficient of drag, it is equal to 1.46 upon root rel. Then we have another velocity profile, which is u by u is equal to 3 by 2 y by delta minus 1 by 2 y by delta whole cube, as per which delta is 4.64 x upon root rex. Then tau naught is 0.323 mu u by x into root rex, and CD is 1.292 upon root REL. Then we have another velocity profile, which is U by U is equal to 2 into y by delta minus 2 into y by delta whole cube plus y by delta raised to 4, which is delta is 5.84x upon root REX, tau naught is 0.343 mu u by x into root REX, and CD, it is 1.372 upon root REL. I'll also tell you which profiles are important to remember for competitive exams. But firstly, just you need to see all of these profiles, that these are the profiles and these are their equations for delta, tau naught and CD. So the next profile, U by U is equal to sine pi by 2 y by delta, which says that delta is 4.796x upon root REX, then tau naught is 0.327 mu u by x into root REX, and CD is 1.31 upon root REL. Then we have the Blasius solution, which is delta is equal to 5x upon root REX, then tau naught is equal to 0.332 mu u by x into root REL, and CD is equal to 1.328 upon root REL. ये हमें याद क्यों करना है? बिकॉज न्यूमेरिकल्स में क्या होगा कि हमें सिर्फ वेलोसिटी प्रोफाइल दी गई होगी एंड विल बी आस्क्ड टू फाइंड कि एवरेज कोएफिशिएंट ऑफ ड्रैग क्या होगा, या तो शेयर स्ट्रेस क्या होगा, या फिर बाउंड्री लेयर थिकनेस क्या होगी. तो ये फाइंड करने के लिए वी नीड टू रिमेंबर दिस इक्वेशंस. अभी इफ़ आई टॉक अबाउट the important velocity profiles that you need to remember, then it is the first one and the last one, because mostly जो है questions इन्हीं में से पूछे गए हैं. If you can remember all of the velocity profiles and their equations, then that's well and good, and if not, तो first और fifth वाली velocity profile के लिए जो है boundary layer thickness, average coefficient of drag and shear stress, ये equations तो you need to remember. Now two topics are remaining. One is what is boundary layer separation, and the other one is methods to prevent boundary layer separation, which we'll understand in the next video. Thank you.